So thank you for the kind of introduction, and thanks for the invitation. It's nice to be back in France. So yes, so this is going back in history for me. This work was actually my PhD thesis, so it's taken some dusting to go through my old papers and try to prepare a new view of what I did now. So I'll try to explain the basics about the differential equations, what the question is, and how to use interval analysis to actually prove something about this. So the Lorenz equations you might have seen, it used to be, it's the example of deterministic chaos. So it was introduced in the 60s by Lorenz as a simplified model of a simplified model of a model. So it doesn't really model convection at all, but that's where it came from. This was the simplest model he could find that still had interesting dynamical behavior from this point. So it's a three-dimensional nonlinear ODE. It has three parameters here, sigma, rho, and beta. And the ones that he picked and wrote about in his article just happened to be the following, so 10, 8/3, and 28. It does matter, of course. If you change the parameters, the dynamics change a lot. 28 could have been 29, so it wouldn't have mattered. However, had it been 31, it would be very different. The pictures would look the same, but the result would probably be false. When you start by looking at this system of equations, you see that it has an inherent symmetry in it. If you flip the signs of the two first variables, you see that you have a mirror symmetry. So that means that if you find the solution for a periodic orbit, for instance, there should be a twin periodic solution, unless it's symmetric. You can also see that it has three fixed points, at least for the parameters we're studying. And R is small, it only has one. Reasonably large rho here, it has three. The origin is always a fixed point, and then you have two symmetric fixed points. C plus and minus, and they're easy to compute. And you can check the stability of these, of course, by just linearizing. So the origin is a saddle with two negative eigenvalues and one positive eigenvalue. And the other two fixed points are unstable spirals. They have a one-dimensional stable manifold, so you get sucked in towards them, but then a two-dimensional unstable, so you get rotated out. So looking at the eigenvalues of the origin, there you have the saddle, so you have a two-dimensional stable manifold, so you can get attracted to the origin plane, and then you get repelled along a line. And it's actually the unstable manifold of the origin that forms the attractor, the closure of that. I'll show you the picture shortly. Well, if we just look at the equation still, you see that it has constant divergence, which is unusual but nice. Okay, so it's just depends on the parameters. Yeah? And for the parameter values we're looking at, sigma equals 10, beta equals minus 2/3, you see that it contracts volumes at a significant rate. So for each time unit, you can basically contract volume by a factor of 1 million. So it's very dissipative. Also, you can find an explicit neighborhood containing the origin that gets mapped into itself by the flow, so a trapping region, so to speak. So that means that you don't have to consider all of R3, the whole phase space. All the interesting long-term dynamics is going to happen in this absorbing region. I'm sure that if you're outside, you'll enter into it and find out. So maximal invariant set is then intersection. I mean, what happens to this set U as time goes to infinity? That's what you want. Well, it has to have zero volume, of course, because of this dissipative force acting. And it also has to contain the unstable manifold of the origin, because the origin is part of it. Okay, so what Lorenz did in the 60s was rather amazing. I mean, he did not have access to the simulation tools that we have today. We had very, very crude computers, but he kind of thought very carefully about it, and he said that, well, these differential equations seem to have, the long-term behavior seems to tend to some attracting invariant set. Every initial point will kind of flow to this set. He also noticed, and this is the butterfly effect, the sensitive dependence on initial conditions. So even though everything kind of tends to the same set, on this set, the individual trajectories will behave very differently. Okay, so if you take two initial conditions very close to each other, they'll follow each other for a little while, but soon they'll do completely different things. So this was a famous butterfly effect, and it's one of the main ingredients in chaotic dynamics. He also reasoned that whatever this set A is, this maximum invariant set, it should have some kind of fractal structure. And this is quite amazing, and when you read this article, it's striking how he analyzed, and using very, very little data, and just thinking about what the flow was actually doing here, he came to this conclusion. And then also he noticed that if I change the parameters in the differential equation a little bit, yes, then the trajectories will change as well. And this attracting set will change a little bit, but it will still be there. It will move a little bit, but it will still be there. So it's robust. So it just doesn't vanish if I change the parameters. I have exactly the same behavior, just a little twist. So in modern language now, he observed what we call a strange attractor. This terminology wasn't available. And here's a little picture of part of it. You see there's lots of white space here. It shouldn't be. This attractor is more than two-dimensional actually. It's 2.06 dimensional roughly. And that 0.6 comes from this fractalness. In one direction it's a Cantor set of positive measure, 0.06. And what I've plotted here is actually, here's the origin, and here are the two branches of the unstable manifold. Due to symmetry, it would be enough to compute one of them, and then you just mirror it, and you get the other branch automatically. You also see these two holes here, that's where the two fixed points are residing. Remember that they're repelling, so you don't really come close to them. You can come quite close to them, you follow in along the stable manifold, but then you kind of spiral out along the unstable two-dimensional. Then eventually you might come close to this two-dimensional stable manifold of the origin, so you approach the origin, but eventually any little perturbation is going to get kicked out by the unstable direction. And he, of course, Lorenz had no pictures like this. This is way out of scope. Okay. So that was 63. People thought a lot about this and tried to say, what can we prove about this differential equation? Because it looks simple, but that's the problem with differential equations somehow. They're too compact, they contain too much information. So what happened later, in the late 70s, was that John Guggenheimer and Bob Williams thought about, well, let's forget about the actual differential equations, let's think about what it does in phase space. What does it do to trajectories? And they came up with this geometric model. So it's completely decoupled from the differential equations. Let's just think about flows now. So they devised this geometric flow that they thought should mimic what the actual differential equations do in some idealized sense. So here's the origin, and you see it has this kind of two bulbs going around, so the fixed points are sitting here, the C plus and C minus. And then they say, okay, let's take a section here, a Poincare section, two-dimensional rectangle, and see what happens when we start flowing a point from there. See where it comes back. And that's what they're trying to, or what I'm trying to show here, is that you can naturally divide this Poincaré section into two pieces, depending on which side of this red cusp you're on. This cusp is actually the part of the two-dimensional stable manifold of the origin. So it will intersect sigma in a line. And you're either on the right-hand side or on the left-hand side. And that will tell you which side of the saddle at the origin you flow. So on the right-hand side, you'll flow this way. And you'll come back, this whole half rectangle then, will come back as this blue cusp. And then by symmetry, the other half will do exactly the same, come back as this cusp. So your return map is actually discontinuous, which it has to be, because there are points on the return plane that never return. Those are on the stable manifold of the origin. They just tend to the origin infinite time. If you're on this side, strictly you will come back into that cusp. If you're on this side, that cusp. And then of course this is just one revolution. Now you can go another lap, then you'll have 4 cusps that are nested, and then more and more and more, and you'll get this canto structure. You see you have expansion, we call this the x direction, you have longer here, and you have contraction in this, let's call it y direction, so you can contract it there. So this kind of explains why you get a canto set in one direction, in the y direction. Okay, now if the flow does this, so you do have, and you can idealize it, so you're actually have your expanding direction is the x direction and your contracting direction is the y direction. But then you can reason and say that any point that has the same y coordinate will eventually have the same future. They'll get mapped closer and closer because you have contraction in the y direction. So they'll kind of have the same infinite future. So we can just collapse this two-dimensional return map that goes from sigma to sigma into a one-dimensional map. We don't care about the y direction, that's not interesting. Okay. So if you do that, you get a one-dimensional map, and you can rescale it, so it's just from the interval to itself. And then, since they're idealizing this, why not give this one-dimensional map some properties? So this is roughly what it would look like. So you see, so it's a blue graph, and I've just drawn some iterates. So if you take an initial point here, you get mapped to here, here, and you go along endlessly. The properties of this one-dimensional map that they get from quoting out the stable direction is that it should be odd. This comes from the symmetries from the differential equations. It should have a singularity at the origin that has to do with the fixed point at the origin being saddle. It should have a negative second derivative. This is actually not necessary, but it just makes everything easier. We'll bumps on it. And the derivative should be greater than square root of 2. This is also just a technical thing. You want your map to be expanding or eventually expanding. This is very expanding. It just made the argument easier. Because if you have these 4 conditions, then you can show that this map is topologically transitive. That means that no matter how, if you take 2 open sets on the interval here, no matter how small they are, and you start following one under f, the iterates of that, it will eventually intersect the other one. It means that you cannot decompose the attractor of this map into disjoint sets. They're all mixing. So they could prove this. Now they made lots of assumptions, but then going back from this result, they could then unfold it again to this two-dimensional return map by unfolding this collapse direction, and then they could embed it in this flow again. So then this geometric flow they showed would have a strange attractor. It would be mixing topologically transitive, it would be expanding in the right direction, and would be attractive. This is what it looks like from above, actually. this line here is intersection. So here we're looking at sigma from above. This is the intersection of the stable manifold of the origin with sigma. It looks like a straight line. It's actually a little bit curved, but you can't see. And these are the two blue cusps. They don't really look like, you can't see them like cusps. They look like lines. And that's because you have this enormous contraction. So you can't really see any details at all. And nor could Lorenz, which is why it's so interesting that you can still make the right predictions. Okay. The problem, so this was a very nice result. So in principle, they understood what this differential equation should do. It should do what the geometric model does, because then Lorenz is right. Then the differential equations generate a flow that has a strange attractor. Problem was that this geometric model was completely detached from the differential equation. There's no a priori relation between them. And then the kind of hunt began. How do you prove something about the differential equation? Can you prove that they actually also have this geometric model features? And the first results came in the late 80s. These are independent works by Clark Robinson and Mark Rushwick. They actually constructed explicit families of ODEs where they could prove that their flows had these geometric Lorenz flow properties. However, these are families of ODEs, so why are they that? Well, they needed to start from degenerate differential equations and have arbitrarily small unfolding of them. And then they could say, for sufficiently small unfoldings, this will happen. And another drawback of this result was that in these families, they did not contain the actual Lorenz equations. You couldn't find the rescaled Lorenz equations and so on. They had cubic terms. Okay, so this really didn't answer the question. Jumping ahead a couple of years, Hastings and Troy together made a computer-aided proof. Proving that something about the unstable manifold. There's a homoclinic orbit, means that the unstable manifold goes out, actually hits a stable manifold. So it forms a bi-infinite loop to itself. Homoclinic orbits are interesting because once you have one of those and you perturb, you get something called a horseshoe, which is chaotic. So they could prove that for some R between 1 and 10,000, I think, or something really huge, there is a homoclinic orbit. In '95, Konstantin Mishaikov and Marek Mrozek, yet another computer-aided proof, showed that in fact the Lorenz equations for a different value of R, not for the classical parameter values, actually has a horseshoe. This is a Smale horseshoe, which is one of the kind of fundamental examples in chaos. So they showed that the Lorenz equations gave rise to chaos. But it was chaos in the kind of weak sense, because this horseshoe is not an attractor. It's just an infinite set of points that form an invariant set. But that set is actually repelling, so you would numerically never see it. So this is obviously not what Lorenz was observing, or anyone else, by the way, when they do simulations. So, and they have measure zero, so it's invisible from that point of view. And this was happening during my PhD thesis. So here's where I realized that this is the way to go, because these were the only ones who could actually prove something about the Lorenz equations. And both of them use computer-aided proofs. So that must be the way to go. Okay, so let's see what we have to prove. So what is a strange attractor? What conditions do I have to verify from the Lorenz equations to prove that it has a strange attractor? Well, first of all, the attractiveness means that there should be some compact set that is mapped into itself under this return map. So we're again looking at the return map going from the sigma to itself. So some set must be mapped into itself, forward invariant. And I'm allowing for this little set of points lying on the stable manifold not to come back, because they just tend to the origin. But everything else should be mapped inside. Okay? What else do I have to prove? I have to prove that we have this sensitive dependence on initial conditions. And that requires, remember that the one-dimensional map has to have a derivative greater than square root of 2. It needs some kind of expansion properties. So I have to prove that some direction in this Poincare plane, some set of directions are going to have expansion. So if I take a tangent vector in these directions, they're going to be expanded when they come back. So that's what we call a cone field. So I'm going to actually put a whole cone, and inside these cones, every vector will get expanded after one return. And the mathematical statement is just that your cone field should get mapped into itself by the Jacobian. And then here comes the expansion. If I take any vector inside my cone field, then it should be, well, this says that eventually it will be expanded. If I take high enough iterates, then this is going to be big. Because lambda is bigger than that. C could be small, but eventually this is going to dominate. So this is the expansion point. So these three things I have to prove. Forward invariance, a cone field, and then expansion inside that cone field. The nice thing about these is that they're open conditions. For a set to be mapped inside itself, you're allowed a little errors. Right? If it's mapped well inside itself, not on the boundary, but well inside, you do some errors. Right? And this is the same thing here with the cone field. It should be mapped inside itself. This doesn't look open, but you can take away this. It doesn't have to be equal here. And these constants allow you to kind of make some errors. So this is kind of robust. So somehow we should be able to use rigorous or set value techniques to verify these conditions. So as I said, the first condition that you're mapped into itself gives you the existence of an attracting set. Attracting set can be very boring from a dynamical point of view. It could be a long, stable periodic orbit, or short, just a periodic orbit that is stable. And of course, a neighborhood around that periodic orbit is going to be mapped into itself. But the other two conditions rule that out, because if you have a stable periodic orbit, then every direction is going to be contracted. So you cannot have this cone field within where you have expansion. That rules that out. And in fact, digression here, when you look at dynamical systems, this is usually the hard part. Lots of papers say that here's a dynamical system, we've iterated it 1 billion times, look at the attractor, look at the strange attractor, obviously it's chaotic. But you don't know that. It could be a very long periodic orbit that is stable. In fact, it could be a very short periodic orbit. It's just that you have 1 billion transients before you get trapped into its immediate basin of attraction. And for the Henon map, which is a two-dimensional discrete map, it's not a two-dimensional equation, this actually happens. We found that for some parameter values, if you iterate 5 billion times and plot, it looks completely chaotic. If you do it a little more, all of a sudden all that chaotic stuff disappears, and you see that you have a period 33 stable orbit. So the whole attractor just vanishes, and all you're left with is some trivial attractor. So that could clearly be the case here. And this is the case if you increase this parameter rho a little bit, we think. So this expansion rate, this lambda and the c that I talked about, if the expansion is strong enough, then I can prove that I have topological transitivity, just like they did for this one dimension map. And then it follows. It is a strange attractor. Okay, then there are some other technical things here. But the main point is, if I prove 1, 2, 3, and a little bit more, then the original Lorenz equations do support the strange attractor. So then he was right. So now I'll try to tell you a little bit how I did this. And by robust, I mean that we changed attractor is going to change, but it's going to have the properties of being a strange attractor still. That doesn't change. Okay, so the strategy then is we have to get information about the return map, this Poincaré map. But to get information about that means that you have to have rigorous information about the flow. It means that you have to solve the differential equation rigorously. So you have to find enclosures of, not only for the return map, but also for its partial derivatives, because we need that to get this cone field and expansion information. That's one difficulty. Another one, which was quite unexpected, was that, remember that the attractor contains this, the origin, where the unstable manifold is. But if you ever try to flow or integrate numerically near a fixed point, you're in trouble, because the vector field is arbitrarily small there, which means that you're supposed to spend arbitrarily long time in the vicinity of that fixed point, because you're slowing down. Numerically, that's bad. So if I'm going to build a rigorous numerical integrator, I'm going to have trouble at the origin. But then you think, well, at the origin it's a saddle, so just linearize. Take away all the nonlinear terms, then we can actually compute explicitly what the flow does. That's kind of dynamical systems aim, any dynamical systems course. Then you can stop integrating when you're close to the fixed point. Then you have explicit formula for what the flow does until you're far away, and then you can integrate it. So why not just linearize? That would be perfect. The problem is that you cannot do that, because when you linearize, you have to do a change of coordinates that is very sensitive to variations in the parameters. Basically, your change of coordinates is not going to exist for dense set of parameters. And that's bad if you want to do something with open sets. Okay, so then the trick is to not linearize. But we almost do this. So we take away lots of bad nonlinear terms, but we keep lots of good nonlinear terms. Then it happens, it turns out, that all of these problems with this change of coordinates goes away. The change of coordinates is well defined in an open neighborhood of parameters. I'll tell you more about this. Okay, so these are the kind of two things. Is to have a rigorous integrator and to find a normal form that is close to linear but not quite linear. It still gives us kind of an explicit description of what happens near the fixed point. So we don't have to numerically integrate. Okay. So Rn, this forward invariant set that is mapped into itself by the return map, we'll split that into lots of small rectangles. And we'll look at one of them at a time. So here's one of them. And I want to see where it comes back to sigma. So what I'll do is actually I'll not try to flow it all the way, but I'll introduce lots of local return maps or cross sections. And I'll just flow it between two adjacent ones at a time. Sometimes I have to switch direction in this plane, if you cannot get the picture. And then, of course, the global return map is just going to be the composition of all of these local maps. So now I'll talk about one of these transitions, going from one plane to another. So that's a distance. These are constant distance, a fixed distance. So like distance d maps. And the fact is, so here we're sitting at the top of one plane, and then we want to flow down to the bottom of the other. And this is our image at the kth plane, and we want to go to k plus 1. And instead of flowing the whole box, which would give you overestimation, you know, if you have big sets, you get big dependency problems. What you can do is you check monotonicity of this distance d map. maybe it's monotone with one or several of its variables. And this happens to be the case. Because then it's enough to just check where the corners go. If both partial derivatives of the map going from this level to the next one is non-zero, you just flow the four corners and take the interval half. Okay. Sometimes maybe there's only one partial derivative that is non-zero, but then still, instead of looking at the whole thing, you just look at the line. And then looking from above then, in this case, where we're flowing the four corners, we have these a priori enclosures. For those of you who have done rigorous integration of differential equations, you know this. So these are just kind of safe bounds. I know that I'm never going to flow out of these boxes going from one level to the next. Then you can see that you can actually see contraction going from one level to another. These 2 points are getting mapped close to each other. These 2 points are getting mapped close. Maybe they're getting mapped further in this direction. So you have expansion in this direction and contraction in that direction. So you can actually pick up hyperbolicity, which is what you want to do. And this is not enough. You also, eventually, due to this growth or overestimation, the little box is soon going to be big when you try to rigorously flow it. And at that stage, when it reaches a certain threshold size, then I split it into smaller pieces. So I start with the box, and it's grown to some size. So this is, the blue thing is kind of, well, the black thing should be the true image after time t. The blue is my overestimation, and then I take the interval hollow back. So you get these kind of overestimations all the time. I split it into 4 boxes, and then I flow them independently. And what will happen is that they start overlapping. Because this is what the flow does. It squeezes in one direction and it expands in the other direction. So you see they get contracted here and expanded there. And then you keep on splitting. So one little box will return as a union of lots and lots of small boxes. And it's a union that is guaranteed to contain the true image of the initial box. And then you can kind of, well, you can map quite weird areas with the union of boxes. So that's how I compute it. So I take one of these small rectangles and I compute and I represent it as lots of smaller images. So after a full return, I come back as a union of many small boxes. So I start with this light blue box, taking a fixed grid here. I come back with all of these grey boxes, and then I find all the boxes in my grid that are necessary to cover that. So I'm covering it by the same kind of pieces that I started. And all the new ones I get, I flow. And then eventually, well, here you can't see it, but it should be light blue boxes covering all of these grey boxes here. Eventually I see that I'm mapped into the whole set. The set is mapped into itself. And then I've proved point 1, that I have a 4-invariant set. And no more boxes that I have to have. It's almost the same thing with the cone condition, this 4-invariant cone, except that it's on the C1 level. I'm working in vector, in the tangent space instead. For each box, blue box in my covering set here, I assign this dark blue cone. And for every little box that ever comes back to that, here's one of these dark gray ones, it will come equipped with a cone as well. And that red cone here must be inside the blue one. That's what I mean when I'm mapping the cone into itself. Okay, so that's basically how we prove point 1 and 2 and 3. Because we can also measure the expansion rates inside these cones when we compute them. So we get that for free. I just want to say something little about this origin equation. Remember we couldn't linearize properly because that was delicate. I'll try to explain why. So we have 3, now I'm switching from x, y, z to x1, x2, x3. Okay? I'm going to use, well, this is just notation. What I want to do, my vector field, I'll linearize it. Well, I'll write it as a linear part and a non-linear part. So x prime is equal to ax plus something non-linear. And I can make sure that this linear part is diagonal as well, because it's a 7. Okay. In the non-linear part, I just want to keep powers of x. So remember, this x to the n is actually x1 to the n1 times and so forth, that are of a certain shape. And this is a shape. So it means that my x1 exponent should be at least p, and the sum of the x2 and x3 exponents should also be at least p. Remember that x1 will correspond to the unstable manifold, and x2 and x3 will correspond to the two-dimensional stable manifold. And I'm basically saying, by only allowing these non-linearities, I'm saying that the vector field should be order x to the p, and it's close to the stable manifold or close to the unstable manifold. That's what I'm saying, if I take away all the others. So what I want to do is I take my original Lorenz equations, here's a diagonal linear part, and here's a non-linear part. This will only contain quadratic terms, actually. But some of them are bad, so I want to throw them away. Then I'll do a close to identity change of coordinates, which will bring it into this good, almost linear form. So it has the same linear part, but a non-linear part consisting of just these kind of flat terms. So G is almost linear. And the P I take is 10. So somehow it works. Now the problem is to prove that this change of coordinates exists and how big radius of convergence it has. And this is a problem in when you linearize, because then you want G to be 0. You want to remove everything. And then this is going to be extremely sensitive. Because when you're computing your change of coordinates, you can write it as a formal power series. These AIs are going to depend on these quantities. So this is a scalar product of 3 integers and the 3 eigenvalues, minus 1 of the eigenvalues. So you have to divide by this quantity. And if this is 0, you cannot solve for your change of coordinates. And if it's small, it's called a small divisor, and you will get convergent problems. But the way I've chosen my G is that then I can prove that none of these are small. So I can always solve for my change of coordinates. And the strange thing is this proof also has to be computer generated, actually, for different reasons. Because you have to kind of compute very many of these coefficients before you can start an induction reasoning. So you can say that all these ones that I want to take away, all the small divisors I'm going to get to have to look at, they're actually quite big. They're not small. 0.01 was the smallest one. And then this is for all orders up to 58, and then for all orders bigger than that, I actually have growth. These are big divisors. It's big, grow linear. So this, to prove this, I actually have to explicitly compute 19,400 coefficients before I can start the induction process. So that just says that I can formally do this change of coordinates, but if I want to know the radius of convergence, I have to prove that this power series actually converges. And now I'm trying to close it down. So you do that, this is a classical way of doing it in complex analysis, the method of measurements. If you want to prove that a power series converges, you prove that the power series with bigger coefficients converges. If that, because that power series majorizes the other one. So it's harder for the other one to converge. So what I get is I just take the minimum of all these divisors over all components, over all orders, and I get a formal power series now for this majorizing function. So I know that whenever this guy converges, my change of coordinates will converge too, because it has smaller coefficients. And again, to actually prove that this converges, you have to compute many of these initially, before you can start an induction process and show that or decreasing fast enough. What you can show is that this does converge on a disk radius 1. And if you want to get some more bounds, if you shrink your disk to radius 1/3, you can prove something a bit stronger, which is what I need. This is technical. It gives me a bound on this good non-linear part. And this bound allows me to actually prove what the flow does near this fixed point. So I can explicitly compute the map. It tells me where points go and where tangent vectors go, even though they're spending infinite time there. And for this, we needed actually almost 200,000 coefficients to start the induction process to get it good. So these are the key ingredients that kind of almost linearizing process and the rigorous numerics, and then gluing them together. That gave us information of the global return map and its derivatives. And that allowed us to do 1, 2, and 3. These three conditions that actually said that the actual differential equations have the same properties as a geometric model. So in retrospect, when you're a PhD student, you're kind of focused on doing this, and I had no idea that there was a world of interval analysis at the same time. So this, I kind of made up my own limited interval analysis just to solve the problem I was interested in. I didn't know that there were rigorous integrators, so I built my own, tailor-made for this. It's a very bad integrator. It worked for this. Again, as I said, I'm really happy I found these articles by Hastings and Join, Shackle and Rozek, because they really convinced me that if you want to prove something about a general differential equation, or a given one, then maybe computer-aided proofs is the way to go. I'm still not convinced that this fixed point is such a problem. Everything is good there. You have contraction in exactly the right direction, you have expansion in the right direction, everything is good, except that you're spending a long time there. I've always had this thought that there should be some easier way than this normal form approach, but I haven't come up with it. The partitioning process that I told you about, that you have this growth of your boxes, so you split them, and then you look at the image as a union of many boxes. This I really believe in. I think there are lots of good ODE solvers now, but none of them really have this partitioning process. I think if you want to integrate big sets, this is the only way you should do it, the only way you can do it, because otherwise the wrapping is going to catch you in the end. I think that this would be interesting to kind of merge with existing software. It would be really interesting to redo all my computations today, because at the time it was just what was doable on the computers. This was the late 90s. I was running it in parallel on lots of Spark workstations. I'm sure I could do it, and it would take weeks to run everything. I'm pretty sure we could do it in 15 minutes on a laptop today, using modern software. That would be nice. And then finally, I should thank my supervisor, Lennart Carlson, and Jakob Pallis, who was a director of INPA at the time, for actually suggesting this. I would not give this problem to a PhD student, but they thought that they could kind of, I don't know, it was a really bad problem to give them, but it worked out fine in the end, so I'm very happy that they did this. And then finally, just some classical reference to what I've talked about today. And I'll give this talk to Luke so we can discuss it as well.
Okay.
Thank you.
Do you have any question?
So, yeah, no question. So I have one question about the robustness. You study the robustness with respect to the parameters.
Mm-hmm.
So you just have taken some very small intervals.
Yes.
And is it possible to study the robustness not only with respect to the parameters, but also to replace your state equation by differential inclusion, for example, very key one
Yes, yes, it should be.
It should be possible. So it will be more general.
Yes, yes. I mean, I did everything except generality in this
Okay.
thesis. I was
Okay.
just kind of aiming to get that. But yes, so I took small intervals containing these parameters.
Okay. So, thank you again.